Welcome to the last talk of the day, 5:30 on a Tuesday, why not? Although it's Vegas, so you guys probably have like 2 dinners and like 6 happy hours between now and whenever you go home. Anyway, my name is Sean Faulkner.
And my name is Cal Rube.
And welcome. This is, essentially we're going to be talking about how to go from AI agent demos to essentially production. I think a challenge that many businesses face today. So first off, how many people here, you just put your hands up, have built some sort of AI demo? You know, maybe it's a single shot prompt, RAG, agent. All right, keep your hands up. And then how many of you have made those demos turn into production use cases? Anybody? Yeah, a few. Great. So this is one of the challenges. And of course, there could be many reasons why you haven't been able to move those demos into production. Maybe the demo was never designed to be a production use case to start off with. But what we're going to talk a little bit about today is our experience working with a number of customers across Confluent as well as Anthropic, and some of our experience where we see customers getting stuck with moving essentially those types of demos and POCs into production. And clearly AI is powering a lot of new experiences. We just crossed the 3rd year anniversary of ChatGPT. There's been such an explosion of technology. Last time I was at reInvent was 2 years ago. I walk around the expo floor today and it's like unrecognizable to where it was 2 years ago, because a lot of those companies either didn't exist or they're very much in their infancy a couple of years ago. Everything's about AI right now. And it has transformed, I think, a lot of how we think about doing our jobs. If we're engineers, we're probably using some sort of AI assistive coding tool, Claude Code, for example. Or if we're generating content, we're probably using some sort of AI-based tool to help us do that. We're relying more and more on these systems. Yet at the same time, a lot of companies are still struggling for where is the ROI for my particular use case, or I want to solve this problem, how do I solve this problem, and I can't get there. I'm still struggling to essentially bring that stuff into production. And while all this is going on, a lot of people believe also that agents are the future of software. You hear lots of proclamations like SaaS is dead, it's all about agents. And regardless of the metrics that you look at, whether it's this chart that's predicting the agent market being 50 billion by the year 2030, or Gartner reporting that they think that by 2028, 33% of all software will have some sort of agent baked into it. It's always hard to make predictions in technology. We tend to overestimate in the short term and underestimate in the long term. But even if you only believe some of this stuff is directionally correct, it's of course something that we all need to be paying attention to when we work in technology, and we're trying to all figure this out right now. And I think the dream or the promise of agents is amazing. Like the fact that we could have some sort of dynamic autonomous system that's doing work on our behalf. Everybody gets an intern in their pocket, really the smartest intern that possible with almost perfect recall. That's amazing. So if we can turn that dream on for our businesses to solve all kinds of different use cases, of course, we want to be able to do that. Now, fundamentally, what is different about these types of models? And broadly speaking, when we look at AI, there's been sort of 2 different eras or waves. We've had purpose-built models, and then now we have foundation models or generative AI, large language models, however you want to kind of term it. And one isn't necessarily a replacement for the other. But there are key characteristic differences between these kind of 2 different eras that's important to understand. So with purpose-built models, or predictive AI, some people might call this is kind of like the AI that I grew up on and was trained in and was a researcher in for a number of years. The way that you build these models typically is you start with your data. So you start with your business data, and you go through this batch offline process of feature extraction, feature engineering. You train your model, you test that model. Once you're happy with it, you can deploy it, and you start using it within your application. And these are served us well for decades, and will continue to serve us well for decades from here. But the sort of limitation of these models is that they're purpose-built, so they're kind of singular purpose. Like once I've gone ahead and I've trained my fraud detection model, I can't just start doing image classification with it. I need to go through essentially a different training process, maybe even use a different type of model, probably different features to go and train that image classification model. So they're limited in terms of their reusability, but the advantage of the models is they know a lot about you because they were trained on your data and they were trained to solve a specific task. So they have a representation of essentially your business baked into the weights of that model. And foundation models kind of have an opposite set of characteristics where they're these massive models that are trained essentially on everything publicly available, and only a handful of companies in the world have the resources and knowledge how to actually construct these models. And they package them up in a nice API that anybody who knows how to call an API can essentially leverage the model. They don't need to know anything about sort of how the model was constructed or the guts of the model to use it. And this has democratized access to AI, and I think led in many ways to this explosion of interest in people building software that leverages AI today. And the other amazing thing is that they can be used for infinitely many things. I can use the same model for many, many different use cases. But the limitation of the models is that as smart as they are about public information and general information, they're kind of dumb when it comes to essentially your business information because they lack that context. They weren't actually trained on your customer data or on the data within your business. So you have to give them that information. So how do you do that? Well, typically that happens during this process of prompt time assembly. So when I'm about to call the API to the model, I need to go and gather essentially whatever additional data that I need to sort of to give to the model so it understands what the task is and it can accomplish its goal. And in an enterprise scenario, this is kind of easier said than done because enterprises have data all over the place. You might have thousands of different databases. You have SaaS locations, SaaS applications where your data might be located. You have APIs, all these things. And this has been these data silos and data fragmentation and just understanding where your data is has been a problem in businesses for decades now. And AI is really just the next sort of forcing function for people to think about deeply what their AI or their data strategy is. Because fundamentally, it's hard to have an AI strategy without a data strategy. Because if your data is a mess, slapping a model on top of it doesn't really solve that mess. So how do you essentially do that? And a lot of this essentially is grounded in this concept of context engineering. I'm going to hand this off to Cal to talk a little bit about how we've evolved essentially beyond the prompt.
All right, thank you. So I joined Anthropic about 2 years ago to help start a team that we call Applied AI. And it's Applied AI's mission and goal to help our customers build great products and features on top of Claude. So when I first showed up at Anthropic, I was meeting with companies from AI native startups to large banks, meeting with their products teams, their engineering teams, figuring out what they're trying to build and seeing if we can do it with Claude, if Claude can solve their problems. On top of that, everyone on the Applied AI team, to make sure we're not just people that talk to customers but don't actually do the work, everyone on the Applied AI team also contributes to Anthropic's products. And so when Claude Code was still an internal tool, I discovered it and really fell in love with it and got to know Kat and Boris and the team and kind of joined that team as like a second job almost. And so most of the system prompt, the tools, all the kind of AI engineering that powers Claude Code, I wrote or worked on in some way. And so between those things, I've had a very nice, I've had kind of the privilege to have a front row seat into how we build on top of these models and get things into production and how this has evolved. So when I joined Anthropic in January of 2024, we had a model called Claude 2.1. Has anyone here ever used Claude 2.1? Okay, no one. That doesn't surprise me too much. Claude 2.1 was not the best model in the world. There were some cool things about it. It was on AWS Bedrock, something that our customers still really appreciate about Claude today. And additionally, it had a very large context window of 200,000 tokens, which many of the other players in the space kind of topped out at about 32,000 or 64,000. So we had a few customers, but things weren't crazy. Then we released Opus 3. Has anyone here used Opus 3? Maybe? One? All right. Opus 3, when we released it, was by many measures the best model in the world, and it really put us on the map and kind of set us off on this awesome trajectory. One thing we believe at Anthropic is we believe we are on this path to build better and better models, and we think this is going to happen very rapidly. And we also believe that this rapid improvement in AI will have transformational effects on society and the world and how we work. And we do a lot of work to study this and research it and get ahead of it. But more practically, as the models have gotten better and as continue to get better, the way we build on top of these models has evolved. So when I joined Anthropic and I was meeting with customers in the Claude 2.1 days and the Claude 3 days, most of the things people were building, not super ambitious, were what we might call kind of single turn prompts. Things like, hey, I need to classify a whole bunch of product reviews, or I need to write a first draft of an email, or we did a lot of this. Here's 3 help center articles and a customer question. Can you like draft a response? A lot of like Q&A chatbot sort of stuff. The model started to get a little better, and people started to get more ambitious about what can we build on top of these LLMs. And we transitioned into what we call workflows. So one thing you could think about doing is you have your single prompts and a bunch of instructions. You could just say, okay, I'll just put more in my single prompt and have it do more interesting, complex things. Well, in practice, that doesn't work very well. The model can, maybe only reliably follow so many instructions at once. And so how do we build something that's more interesting and rich that we can't get done in a single prompt? Well, we try to decompose this task and split it up and chain multiple prompts together and maybe mix in some deterministic logic to get something more interesting and rich than we could have in our kind of single turn architecture. And so if you have used AI features and products, even today, if you were to peer under the hood, probably a lot of that stuff is powered by workflows. Now, workflows in practice have 2 problems. One of them is that workflows are really only as good as kind of all the edge cases that you've kind of planned for, right? Like we have kind of this predetermined like set of things that this workflow can do. And that doesn't work very well for open-ended tasks. So if you're trying to build an AI system that can just do day-to-day software engineering for you, very hard to build that in a workflow. I've met with customers and seen customers that have workflows that are made up of 50 different prompts. And it can be very challenging to kind of manage this and keep this under control. The other thing that is tricky about building as a workflow is that if something goes wrong in the middle of this workflow, you're on LLM call 2, and something, unexpected happens, the LLM makes a mistake or something like that. It is very hard to build any sort of like error correction, or the workflow like notices something went wrong and can kind of like self-correct. And so starting late last year, and certainly this year, we have moved into, for many problems, building on top of a different architecture. Anthropic, this is what we call agents. And with an agent, in many ways it is much more simple, but we take our LLM, we give it a set of instructions, and we give it a set of tools and some sort of open-ended task, and we basically say to the LLM, work on this task, call these tools as much as you want, let me know when you're done. And this helps with our open-ended problem because we don't have to code for everything ourselves. We let the agent kind of figure the problem out on its own. We trust it to do it. We're giving it agency. And on top of that, if things go wrong, the model calls a tool and it gets back a response that it didn't expect, or it gets back an error, the model can see that and react to it and adjust its course and try again. And so it gives you a lot more of this reliability. And you can build more rich, robust kind of products and applications on top of this architecture. And so at Anthropic, we see both of these kind of setups in production today. They're good at different times. We have workflows when we have more narrow, very repeatable, maybe we want to mix in a little deterministic logic tasks. And then we use our agents when we're building more kind of open-ended, broad, working on those sort of problems, and maybe we have a set of tools and things can go wrong, and we're trusting the model to deal with more ambiguity.
Great, thank you. So as we've evolved from sort of this single call shot prompting into agents and workflows, this has also, I think, represented an important shift in how we think about engineering and a shift in sort of architecting software. So with traditional software, we essentially encode the business logic of the software using precise logic and rules. We're writing essentially that code. I click on a button, something happens. That has been predetermined and essentially baked into the software. But with AI systems, what we're doing is, since we're relying on these probabilistic models to make certain dynamic decisions, we're essentially steering the model with the data and the context that we feed into the model. So in a lot of ways, the business logic essentially becomes a output of the data and the context that we're feeding into the model. And represents a shift where instead of software necessarily being precise logic and rules, your data pipeline in a lot of ways becomes kind of your software application. And the same change is kind of happening in the world of testing, where with traditional software, we use unit tests, we use system tests where we can deterministically test the software. But now we're moving into this world of evals where we're using probabilistic tests against the AI systems. And with unit tests, we don't necessarily need to test our software using a real data, because essentially the same input's going to generate the same output. It can be deterministically run. If the unit test pass, we have some level of confidence that the software is going to run as expected once we put it into production. With AI systems, it's hard to do that without some representation of the real data, because the data is such an important input to orchestrate or sort of steering the model in a particular direction. So we need to be able to essentially evaluate in batch, offline, using some representation of the real data. But we also need to be observing these sort of in real time and also continuously evaluating the AI system against the real reflection of the data to have some sense of reliability of the AI system. So with traditional software, we lived in a world of iterating on code. And with AI systems, we're essentially moving into a world where we're iterating on data all the time. We need to iterate, sort of process, reprocess the data, and test and eval, and get to a place where we have some level of confidence this AI system is going to do what we expect it to do. And talk more about sort of all the components of this, like why context matters, what are all the elements of context engineering. I'm going to pass this back to Kyle.
Okay, so remember when we were doing single turn? Back then, we weren't really, the models weren't very smart, and we didn't quite figure things out, and so I would call this the era of prompt engineering. Last year, when I was here at reInvent, I had a whole kind of talk where I was talking about prompt engineering best practices. And prompt engineering was all about, okay, the model's not very smart, so I got to think about how exactly do I craft my instructions in a way where I get something useful out of the model on the other side. There are all these tips and tricks like, how many examples should I use? And if I'm using Anthropic models, I better wrap everything in XML tags. I think that'll make the model work a little better. And so when you were kind of building on top of single turn prompts, what you were thinking about was, okay, what do I put in my system prompt? What do I put in my user message? There was a time at Anthropic where one of the pro prompt engineering tips was never use the system prompt for anything, because Claude was anecdotally a little better at instruction following if it was in the user message. And so there's all these kind of little tricks that people would kind of think about and try to iterate on and test. Now, we are in kind of the agentic world, and so we have moved on from prompt engineering to what we call context engineering. And we kind of think of this as a more broad and interesting problem. Why? Well, we have our system prompt and user message just like before, but we have other things that we want to think about. Now we have our tools, and if we want to maybe give our agent access to documents and other pieces of text, how do we do that? And then remember, the agent is the LM running in a loop. So it's not just one single API call to the LM. It's going to be calling the LM. It does something. You go do something else. Then you give it back to the LM, and it's running a loop and going and going and going. So we have the assistant message. What does the agent say? And we're going to have all of our tool calls and results. And this is going to build up over time. And then maybe to mix things up, we want to add some new tools, some new documents. And so the problem space, what we need to think about and work on when we're building agents, putting them into production, a little more interesting, a little more fun than prompt engineering, in my opinion. So that's what I'm going to be talking about. So prompt engineering, back in the day, models weren't super smart. They were very, very sensitive to exactly how you phrase things and worded things, what words will get me the absolute best output. Context engineering, much more about just managing this whole information environment. What tokens, what am I going to present to my agent and when, and how am I going to do it? What is the optimal configuration of context to get my desired behavior out of this system? I've said context a few times. It's worth mentioning that when I say context, I mean the context window. So all LLMs, whether you're using Claude or ChatGPT or Gemini, they have this context window limit. And this is actually enforced at the API level, but there's only so much text or so many words you can pour into the LLM and get a response back. And it's not that we don't know how to do the math, where if you gave us 10 million tokens, we wouldn't know how to process it. It's more about that the LLM, at some point, we start to see diminishing returns, or if you pour too much text into the LLM, it starts to get confused and do a bad job. So we have to set some thresholds where we think it's an appropriate time to just say, hey, you shouldn't be passing any more tokens to this model. There's this idea of context rot, which is, okay, we have all these tokens, all this text that we could put into the model. I kind of hinted at this earlier, which is we could take all these instructions and give it to the model. We could take a whole bunch of documents and give it to the model. Well, what we find is in most use cases, if you just start dumping text in there, the model tends to do a little worse at whatever you're going to ask it to do. And so even before you hit this context window limit, you want to be mindful of, okay, when my agent is working, when it's calling tools and getting responses back, the initial instructions, I don't want a lot of extra junk in there because it's probably going to be impacting performance. There's a company called Chroma. They did a very nice technical report. It's a blog post. Look it up. They write all about this. And they actually kind of break it down and talk about different ways that this can fail. The other reason you're going to want to think about context, especially when you're building agents, remember I said that an agent is the LLM running in a loop, multiple calls over and over again, is if you build your agent in the right way and you're thinking about context, you can take advantage of things like prompt caching. The idea with prompt caching is if you make an API call to an LLM, and then you make another call and there's some sort of fixed prefix, like the text didn't change from one API call to the next, Anthropic can cache it behind the scenes, and then we can pass on a very nice little cost discount to you, as well as you benefit from some latency because we don't have to process these input tokens again. And so if you are building with context engineering in mind, you can take advantage of these things. And so when we talk about context engineering, we're really trying to kind of move three different levers. One of them is very practical and boring. It's the fact that our API will only let you pass so much text into it at once. So we need to think about, okay, how are we going to deal with this context window limit and get around that and still get our system to do cool things? We can reduce context rot, which is this idea of even after we've kind of, when we're giving stuff to the model, can we make sure the tokens that we're showing it are useful and we're not hurting our accuracy in some way? And then finally, if we do this right and we are mindful of prompt caching, we get some nice cost and latency benefits. And so we do all these things in our own products when we're building Cloud Code, and we advise our customers to do this as well. What are some other things we can think about when we're doing context engineering? Well, we have our system prompts, the instructions that we're going to give the agent, the model. We have our tools. Okay, what is our agent going to be able to do? How can it interact with the world and pull more information in and change things? We have data retrieval, which we're going to talk about a lot, which is, okay, this agent is only going to be as useful as kind of the information that wasn't pre-trained into it. How do we pull things in about the business, about the problem, about the customer, so that it can make smart decisions? And then I'll talk a little bit about long horizon optimizations. If we're building an agent that might work for minutes or hours or days, we're going to have to do some fancy stuff to get around some more practical limitations like the context window, which is going to fill up. So let's start with the system prompts. And when we talk about prompting today, when I'm meeting with customers and talking about prompting, it's less about, okay, should I format my prompt as JSON or Markdown, or Cal, should I be using XML tags and where should I be doing it? We're at a point where we've done so much work to make the models steerable that the little tips and tricks around XML tags don't matter so much. So when people ask me, hey Cal, what's like your best prompting tip? I always tell them that the best tip I have when you're writing a prompt for an LLM is you should take that prompt and imagine you are giving it to your friend or your coworker that doesn't know what you're working on. And you say to them, hey, with this prompt, with these instructions, would you be able to do this task? And if they say yes, then probably the LM can do it too. And if they say, no, I'm a little confused, I don't really know what you're asking me for, probably the LM is confused as well. My team, what we do is we go meet with customers, and very often a customer will say something like, we tried Claude, but like, I don't know, it didn't really work that well. I don't think we want to use it in production. And always what we'll say back is like, oh, okay, that's fine, but like, can we take a look at the prompts? Like, we might be able to help. And 9 times out of 10, when we go and look at the prompts, there's something confusing in the instructions, and we can go in and point it out and clean it up and fix it, put that into production, and all of a sudden, Claude works well. And so there's kind of 2 failure modes, even if you write good instructions, where things can go wrong. So one example of this is I was working with a customer that was building a customer support agent. And what they did at the very start in their kind of POC is they took the standard operating procedure, the SOP, that they give their human support agents when they onboard, when they start on the first day. It's about a 32-page PDF. They copy-pasted it into the prompts, and then they came to me and said, hey, this isn't working very well. And I was like, oh my God. And so this is where you can get too specific. If your prompt starts to look like something on the left, where you have like this complicated workflow, and especially if you have all of these if-else statements, you have this very complicated chain of instructions that goes on and on and on, especially for thousands and thousands of tokens, you're going to overwhelm the model. It's not going to be able to do this very well. And there's techniques and ways to get around this, but this is probably not what your prompt should look like. On the other side, you can fail by being too vague, and this is what I talked about earlier. You give the prompt to your friend, and they're like, I don't know what you're talking about. I don't know how I would do this task myself with these instructions. And so when we think about prompting, we're kind of trying to get into what we call this Goldilocks zone, where we have just the right amount of details, but we're leaving things open-ended and letting the model do what it does best, which is deal with nuance. We're not trying to like hard code in a workflow. We're trying to give agency to the model so it can kind of work. And we want to just be telling the model like, you know, the general way of how it's going to solve this problem, and then the like non-negotiable things that it absolutely must do or absolutely shouldn't do. And then everything else we should try to let it figure out on its own. So it can be too prescriptive. Signs of that is if we have a whole bunch of if-else logic, we have these very complex and brittle instructions, and we're trying to like encode every single possible scenario into the instructions. And then of course we can fail on the other side, like I said. That's the system prompt. Okay, what about tool design? So we have our instructions in the system prompts, but we're also going to give our agent 1, 2, 10, 50 different tools. How do we do that well? Well, we want to remember that the tools, when we give a tool to the model, we should just think of that as additional prompting. What happens behind the scenes when you make an API call to Anthropic and you pass the tools array, we take that tools array, we actually just plop it at the top of the system prompt, and it says something like, hey, Claude, here's the tools you can use. And Claude's been trained to kind of know what to do from there. But when you're defining these tools and passing them in the API, you got to remember that those definitions are going straight to the model. It is seeing what you are typing in there. And so there's some things we can do here to make sure that we do well. So one is we want just simple, accurate names. Search customers. We don't want something that's just like, I don't know, XYZ123. We want detailed and well-formed descriptions. And we can do things in our descriptions. Think of it like more prompting. We can do things in our descriptions like provide examples, like here are good times to use this tool and here are bad times to use this tool. When I was working on Claude Code, I was very often not messing with our system prompts, but I was spending most of my time in tool descriptions tweaking kind of the prompting and instructions there. One failure mode that can definitely happen when you're building an agent that's more general purpose and can do a lot of things is in Claude.ai, which is our kind of like chatbot tool that we sell to enterprises. We had one team that was off building a web search feature at some point. So they had built this tool that was something like Search Web. And meanwhile, another team was building out our Google Drive integration. So they had built this Search Drive tool. And these, both of these things were working very well. And we shipped these at around the same time, and we kind of put them in, the model now has the Search Web tool and the Search Drive tool. And all of a sudden, the model there wasn't very good prompting here. And so the model was confused about when to use which tool and when. What information would be hiding behind a Google Drive and what would be behind the web. And so the model would be searching for things in Google Drive where clearly it should be using the web and vice versa. And so if our tools, the names and descriptions, especially on search is where we've ran into this the most, are too similar, you can get into trouble and confuse the model. Okay, data retrieval paradigm shifts. So back in the day, back when we were building single turn prompts and workflows, the way you would give the model information about things it wouldn't know about because it wasn't trained on it, wasn't in the pre-training set, was you do this thing called RAG, retrieval augmented generation. The basic idea here is you have a step before you call the LLM where you go try to grab all the potentially useful information and then you give it to the LLM and you say, here's the information, try to answer this question, good luck. RAG has a problem, which is if you fail the retrieval, if you do a bad job at retrieval, there's nothing the LLM can really do about it. If you give it kind of junk data, it can't really recover out of it. Agents solve this problem because we can give the agent a search tool and the agent can write a query to run a search, get some results back and think, oh, weird, I didn't get what I wanted, let me try again. So that's sort of like I talked about earlier, the ability to kind of recover out of errors and kind of bad states. And so in an agentic setup, when we're context engineering, we're always thinking about, okay, what do I want to preload into my agent? What do I want to always be there? Probably the instructions and the tools. And what information can I kind of hide away and tuck away behind my tools? And the agent can go grab it only if it really needs it. So in Claude Code, for instance, if you use this tool, we have something called claude.md. This is like a special markdown file that is optional, but we let our developers basically put in additional information and instructions and preferences that are unique to them about how they want Claude Code to behave and what they want it to kind of know about themselves or the code base. And so something like that, we preload no matter what. When the agent starts, we just look in the current working directory for a claude.md file. If it's there, we put it in the system prompt and we literally say something like, hey, here's some additional instructions this developer wanted you to know. So that's something we preload. But what we don't do in Claude Code is when we start it up, we don't take all the files in the code base and just dump them in the prompt and say, hey, here's all the files in this code base, good luck. Instead, we give Claude 2 tools to basically just kind of grep and find and search a code base like you or I would. And so we're thinking about ways we can do progressive disclosure. How do we kind of give the model hints about, okay, what information might be available to it, and if it thinks it's interested, then it can go and look things up and figure out more about it. Has anyone here heard about skills? Yes. So skills is kind of building on this pattern. We saw this in Claude Code, where we could take files that might be interesting at some point and let the model kind of figure out and use them over time without having to load all the information up front. And so this is really what skills is under the hood. So skills is like this idea where you as the end user basically define, markdown files, Python files, things like that might be useful for the agent at certain times. So in Claude.ai, a good example of this is we want Claude.ai to be able to, make a PowerPoint or build a spreadsheet. But we don't have to take all the instructions for making PowerPoints and making good spreadsheets and put it in the system prompt all the time. Instead, in the system prompt, we say something like, hey, if the user asks you to make a PowerPoint or build a spreadsheet, you go look in the skills folder and there's going to be a whole bunch of useful stuff in there for you. And so in the 10% of the time or whatever where the model, where the end user is going to ask for this, the model knows how to go explore and get that information. And then the last thing I want to talk about is long horizon tasks. So remember we have this context window that's going to fill up. And remember that the model is running in a loop, API call, API call, API call. And we don't want to bust the prompt cache. So that means we're not ever going to remove text from this conversation chain. We're going to be append only. And so at some point our conversation is going to get too long and we're going to get to 200,000 tokens. And what do? Well, in Claude Code, the way we solve for this is something we call compaction. When Claude is getting close to the context window, we can detect this, and what we do is we basically inject a user message in, and the user message says something along the lines of, hey, I need to pass this task off to another developer, summarize everything we were just working on and all the important details. And then we take that summary, we clear out the whole conversation, so we start over fresh. We put that summary at the very start, and then we say, okay, keep working from here. But there are other ways to solve this, more experimental. Memory, can the model just write notes for itself? And then also sub-agent architectures. So system prompts. How do we get the instructions in the right shape? Tools, probably the most interesting and useful things that the agent can do. Think about iterating on the tools. Data retrieval, which we'll talk about. How do we get the right information to the agent to do useful things? And then being mindful of long horizon optimizations if we're building an agent that's going to work for many minutes or hours.
Awesome. So I'm going to dig into this kind of data retrieval challenge and how do you curate context. So if we kind of pause for a moment and we think about like human reasoning. So if you were going to cross a street, how many people would feel comfortable crossing a street based on essentially a snapshot of where the cars were on the street yesterday? Like most of us probably wouldn't feel confident about crossing that street. And when it comes to like human reasoning and decision making, something as simple as crossing a street, like obviously we have a lot of history of doing that. Like I've probably crossed the street successfully tens of thousands of times in my life. But I don't just rely on my historical reference. I also need essentially a fresh representation of what's happening in the moment. So I need to pair essentially both sort of real-time signal information or what's happening in the moment or fresh context with historical pattern matching and so forth. And this is true of most sort of human reasoning situations, but it's also true of most operational use cases when it comes to software, dealing with customers and so forth. So these are important things to think about. And this is in many ways what the context problem is when it comes to data retrieval. Because during this kind of online process of prompt time assembly, I need to go and gather this contextual information. And if my AI system is doing something like helping doctors or nurses monitor patients, I don't want that AI system to be making decisions based on vitals of the patient from 6 hours ago. I want it to be making decisions based on what's happening right now in this moment. But that's a hard problem in many businesses. But there's a couple different ways or different approaches that I see businesses trying to tackle this problem. So the first thing is essentially taking all of their operational data stores, whether it's a database, an API, some sort of SaaS application, and throwing MCP in front of it. And I actually had a call very early this morning with a company that is attempting this approach. And it makes a lot of sense. It's like, let's take all of our operational sources of truth, and we'll throw MCP on front of it, and we'll use tool calls into it, and we'll get sort of the latest information about our business estate. But in practice, there's a number of challenges with this. And it has nothing to do with MCP. MCP is great, but what you're doing when you sort of open up all your different locations to a new workload like this is you're adding a pretty large security footprint on these existing systems that are probably all have their own ways of governing access and access control. So that's one problem you need to solve. They're also probably serving other workloads within your business. So you're adding a bunch of new operational load to these databases and other systems. And probably one of the biggest challenges is that none of these systems were ever designed with the idea that an AI system was going to use them. They were designed for humans to use them. So if I'm designing an API and I'm an engineer that's going to do some integration with that API, well, I can read the documentation, I can read the API spec, and I interpret it and I write business logic that allows me to use that API. Maybe I'm only using a subset of the data, or I need to write code to translate that data into a different format. Whatever it is, I have the context to understand that raw data. But the model doesn't. So what you need is not the raw data, because the raw data ends up with this problem of exploding token costs, where we're feeding a lot of information essentially on the ingress in the model, and then we some mistakes. What you need is refined data or a derived data set. It's like we don't put crude oil into a car. The oil goes through a refinement process before we feed a car and end up with fuel. Or we don't take a bunch of raw ingredients like take salt and pepper and spices and a bunch of raw vegetables and so forth and jam them in our mouths. Maybe you do, I don't know. But usually you go through some refinement process. You cook it together in certain quantities to derive a data set or derive essentially a meal. You go through a refinement process. The same thing needs to be applied when you're building AI systems. You need to essentially refine the data, come up with curated data. So once you realize that this problem, where do you go to get derived data? Well, there's a place where many businesses already create derived data sets, and that's typically in the lakehouse or the data warehouse, where they're already taking a bunch of their operational data, they're sort of throwing it left to right through ETL into the lakehouse or the warehouse, and then they might be going through like a medallion architecture of bronze, silver, gold, and defining a data product. And that data product's used to feed dashboards and so forth. They can reverse ETL that out to some operational database, maybe throw MCP in front of that, and then have their agent talk to it. So this solves the problem of getting derived data, but it introduces a new problem. And the new problem is that this is just too slow for most operational use cases. So it carries all of the same challenges that ETL carries with it, where you have different batch pipelines delivering data at different stages, maybe it's 60 minutes, maybe it's once a day, and you're combining that data in some fashion where it represents, essentially, your data is only going to be as good as the slowest pipeline. A lot of times that data is thrown raw, so into the lakehouse, and the data engineer team has to figure out how to reverse engineer it and understand what the schema is, the lineage, and so forth. Ends up with a lot of reprocessing, remodeling, and a bunch of cascading downsides. But we've been using this to essentially feed dashboards and reports. But it's a challenge when it comes to trying to feed AI systems, especially in the operational use case. I mentioned patient monitoring. There's very unlikely that you'd be able to build a system that goes through this process that can monitor patients at sort of the level of the latency that you'd really want to be able to make accurate decisions. Similarly, if we take like an example from airlines, if I'm interfacing with a customer service bot that's powered by an AI agent and I want to rebook my flight, well, that agent needs to know what flights are available right now. And in essentially the foreseeable future, can't make decisions based on a report that was generated a day ago. It also needs to know my itinerary, my customer my preferences, maybe my status. All this stuff needs to be as fresh as possible. So how do we sort of marry these worlds of having both fresh data and derived data? That's really the key problem. So we need a derived data set that represents the current state of the business. And we can do that using a combination of technologies. So streaming data capture is really good at essentially capturing data as it's generated, real-time data, using technology and tools like Kafka. We can use stream processing, in particular Apache Flink, which helps you essentially bring both sort of data at rest or batch data together with real-time data. It just essentially batch data is just bounded streams versus unbounded streams. So we can combine that data in the stream to create these derived data sets using stream processing technology. And then we need some way of serving that data. And ideally, we have one layer of governance across all of this. So at Confluent, we've been working on this problem for a number of years. And a couple of years ago, we launched a product called TableFlow, which doesn't quite address this problem, but kind of starts to address some of the challenges. So TableFlow was designed to try to bridge the gap between the operational estate and the analytics estate, where we can do streaming data capture, we can use stream processing to clean the data sort of as close to the source as possible, create these derived data products, and then materialize that data as iceberg tables or Delta Lake tables directly into your analytics platform, and kind of taking out the ETL process. And this is great for sort of bridging the gap, and it can also work both ways, where as you create data in the analytics estate, it also writes back out to Kafka so you can serve your operational use case as well. But still, a columnar store is probably not the right sort of data layer for context serving. So what we launched a couple of months ago is what we call the real-time context engine, where is TableFlow, you're taking a Kafka topic and materializing as an iceberg table or Delta Lake table. With the real-time context engine, what you're doing is you're taking your Kafka topic or your derived data set, and you're materializing it as a fully managed, materialized table that's managed by Confluent Cloud, and then is served as a tool over MCP. So that way, from data creation to serving is very, very low latency. and it's designed essentially for feeding these AI systems. And the AI system doesn't need to be running on Confluent. It can be running wherever you want externally, and it doesn't need to know anything about the streaming architecture. It's just talking MCP. And this is one of the core components of something that we call Confluent Intelligence, which we launched recently as well. And the other two core components of that is streaming agents, which allows you to build event-driven agents that these aren't chat-based agents. These are essentially system-triggered agents that react to data as it's being generated within the stream. And then also built-in ML functions or statistical models for doing things like anomaly detection, forecasting, and fraud detection. And all this runs on Confluent's data streaming platform. So you can do your streaming data capture. You can define these data products. Then you can materialize those into your analytics systems, as well as power these different AI systems or streaming agents running on Confluent Cloud. All right. So let's get into a couple demos. So I'm going to walk through two different demos. The first one's pretty simple. What we're going to do is just show off sort of how some of this concept of the real-time context engine works. So I'm going to take a couple different Kafka topics. I'm going to materialize them as tables, and then we're going to use Claude Code to talk to the MTP server, and I'll kind of walk through that. So what we have here is we have a Kafka topic that represents customers. We have orders that are being made by those customers, and then we're using Flink to combine those into an enriched orders Kafka topic, and then we're serving those as tools over MCP. And then we're going to essentially use Claude Code as our MCP client to talk to it. All right, so here on the left we have Claude Code, and then there on the right we have Confluent Cloud. And you can see on Confluent Cloud, we're just looking at the customer's Kafka topic in a particular event that was created. So the first thing I'm going to do is I'm going to ask to show me the topics that I have access to. So Claude's going to essentially reach out, and there's 3 different tools available within our MCP server. One allows you to pull back the tables, or essentially the topics that are being materialized. Here we have customers, we have orders, and enriched orders. All of these have descriptions so that MCP clients and Claude can understand what these actually mean. And then we can ask for details, in this case, about the customer. So we have table lookup, essentially metadata or schema lookup for these various tables. And then we also have essentially point in time lookup. So we can look up this customer information of Joe in this case. So pretty simple. And you can see that matches the information on the right. Not groundbreaking. You could probably do the same thing with a database. But the key here is that as we generate new data, essentially it's immediately reflected here. So we will fully manage this. As new data gets generated, it will automatically get upserted and re-indexed. Or if you need to change essentially the data model, you can handle those kind of reprocessing steps of batch up, essentially completely remodeling the data into a way that's actually going to serve your use case. So we cleared the context here. So now we're going to say, show me the last order placed. In this case, it's going to make 2 different tool calls. It's going to ask first for what tables are available, because it needs to know what tables are there, and then it's going to do the point in time lookup to pull in the orders placed by this customer. All right. So the next thing we're going to do is we're going to go over to Confluent Cloud, and we're going to generate a new event to update this customer's email to show how sort of updates work. So we're going to produce a new message. But what you can imagine here is if you had some customer profile page on a website, I could go into that page, update my email, click save. That's going to write as some event into a Kafka topic that I probably then do a database update at some point as well. But as I essentially send in that new message, behind the scenes, we're taking that data, we're going to upsert it into the materialized table, re-index the table, update the index, and then that's immediately available through MCP for the AI agent to consume. So we're producing that message now. You can see that it's a new message there. And then once we go back over here, we're just going to clear the context and ask to show the customer record again, the details of the customer. So there's really because this is all built on the data streaming platform too, and sort of Kafka as the basis for that, and Flink, these are really designed for really extreme high load and low latency use cases. So it doesn't matter how complicated your data is or how fast things are updating. Essentially, you can combine that in whatever way you want, mix it however you want to create these dry data sets, and it's going to be instantly available to your AI systems. So there we see the new email, and then we can continue to do this to show the latest enriched sort of view of this data and so forth. All right, so let's go to the next use case. So the next one is an application for robo-taxi customer service. Actually, before we came up here to talk, we were talking about Waymos and what's the Zooks and all the autonomous drivers. Well, this is the next iteration of this. This is river robo-taxis. So these are like Waymos, but for riverboats. So imagine you're on the Mississippi in New Orleans, you pull up your river robo-taxi app, and you book essentially a riverboat. That riverboat comes and picks you up. So we're not going to talk about the fleet management. What we're going to talk about is the customer service part of this. So with the river robotaxi, there's going to be different spikes that happen in terms of ride requests, and they need to take certain actions. Maybe they need to dispatch new boats to the area and so forth. So what the scenario here is that I've ordered a boat, but it's taking longer than expected to arrive. I'm sure anybody's ever ridden an Uber minute. One Uber minute is really like 5 minutes. It's very frustrating. But so with this, what I can do is I can go into the River Robotaxi mobile app, start a chat with customer service, which is powered by an AI agent, and I want to know where is my boat, what is taking so long. So in order for it to be able to understand and correctly contextualize response, it needs to understand the ride requests, the volume requests, what decisions have been made, vehicle location telemetry that's kind of streaming off of these different riverboats, customer profiles all need to be taken into account. And what we're going to do is essentially use the context engine to serve this data to the AI agent, which in this case was built using LangGraph, running on AWS, and using Claude as a model. All right, so let's cue that demo. A little magic happening behind the scenes here. All right, there. So this is our various Kafka topics here. We have different topics that we want to essentially materialize through the context engine. So we have completed actions, which represent decisions made by robotaxi for dealing with spikes in ride requests and so forth. And we're just going to enable the context engine for these. And we can do the same thing for ride requests. Once we've done this, these are immediately available as these materialized tables that can be consumed over MCP. I go over to the river support, and I ask about my ride. On the left, you can see the sort of chain of thought reasoning that Claude's going through to get essentially the customer profile, and then also get the decision that was made about why that there's a delay going on right now. It uses that to contextualize a response back to the user, letting them know that they're aware of a delay. They've dispatched new boats to the area to deal with it and to please be patient. But the only way it's able to make a decision like that, or essentially be able to create a response like that, is it needs access to that fresh contextual data to be able to do it. And this is, again, true for most of these kind of operational use cases. Oops, all right. Well, I just said next steps. All right, let's talk next steps here before we get into questions. So if this is of interest to you, and you want to play around with some of this stuff, you can check out our Streaming Agents product. You can also do, there's a workshop that's going on with this. There's a quick start you can also use if you want to sort of do the self-guided tour. And you can try this all out for free using Confluent Cloud. You get $400 worth of free credits for the first 30 days. I'll pause for a minute as people take pictures. And the last thing here is just this week we launched Confluent Marketplace, which is a marketplace for seeing all these various community connectors and a whole bunch of other community-driven projects that you can use within Confluent's data streaming platform. And this allows you to ingest data from pretty much anywhere, any kind of source system within the enterprise. Really cool project. And you can try that all out for free as well.